Here are the top 10 things you need to know about polynomial functions. Must know number 1. What is a polynomial function? Let's start with the definition. A polynomial function is a sum of terms where each of the terms is a power of x multiplied by a coefficient. And the general structure of the equation of any polynomial function looks like this. Now this structure looks difficult, but if I show you a sample equation, you'll see that polynomial functions are actually quite simple. Within each of the terms of our polynomial function, there is a power of x, where x is our variable, which I can see over on this sample equation. And then multiplied by each of those powers of x, we have these coefficients which are represented by the parameter a. And those coefficients can be any constant value. They can be any real number or even any complex number. And the exponents on the x's, they go from n and then keep decreasing until you get to 1 and then finally an x to the 0. Those exponents have to be non-negative integer values. And you can see over in our sample function, the exponents on the x's are all non-negative integer values. And then because this n represents the highest exponent on any x, we know that this term would be the highest degree term. It would be degree n, making the whole degree of the polynomial degree n. So looking at the sample equation, the highest exponent is 4, which means the degree of that whole polynomial is degree 4. And then another important characteristic of any polynomial function is the value of what we call its leading coefficient, which is the coefficient of the highest power of x. So over at our sample function, this is the highest degree term, and its coefficient is -2. So the leading coefficient of that function is -2. And those two pieces of information actually tell us a lot about what the graph of this function will look like, and we'll look at that throughout the next few sections. And then the last part of a polynomial function we should talk about is the last term, which notice does not have a variable x with it, which means this last term is constant. And graphically, that would show up as the y-intercept of the function. And one other thing I want to note is that all polynomial functions are continuous. They don't have any restrictions on their domain. And if I were to show you the graph of this function, you'd see that what we have is a continuous function with no restrictions on the domain. And now let's analyze a quick table of values for this function. I'll choose x values between -3 and 3, and then subbing those x values in for the x's in my f at x function, I could calculate the y values. And now I want to calculate the finite differences between each pair of consecutive y values. Within each pair, I want to do the bottom number minus the top number. So -10 minus -115 is 105. And then for the next pair, 5 minus -10 is 15, and so on. Now these are what are called the first finite differences. They're not constant, so that means my polynomial function is not degree 1. So I can then calculate the second column of finite differences by finding the difference in each pair of these values, still doing the bottom one minus the top one. The second finite differences are not constant, meaning it's not a degree 2 polynomial function. But I'll calculate the third finite differences, and finally, the fourth finite differences, so that I can see for a degree 4 polynomial function, the fourth column of finite differences are going to be constant. So a general conclusion would be that the nth differences of a polynomial function are constant. Must know number 2, end behavior. In this section, you're going to learn how to describe how a function behaves at its extremes. So basically, where does a function start and where does it finish? And before we can do that, let me remind you about how we number the quadrants of a Cartesian grid. Starting in the top right, we have quadrant 1, and then we rotate counterclockwise to quadrant 2, 3, and 4. I'll shrink this and move this out of the way so we can have it as a reference as we go through this section. Now there are 4 types of end behaviors that a polynomial function could exhibit. Now let's say we have a polynomial function that is an even degree and has a positive leading coefficient. I'll short form leading coefficient with the letters LC. If the polynomial function has those two properties, I know its end behavior, meaning I know where the function starts. It would start up in quadrant number 2, and it would finish in quadrant number 1. Now, there are lots of different shapes that it could make between those end behaviors, but if these two criteria are met, I know that this is where it starts and this is where it finishes. So we could say its end behavior is from quadrant 2 to quadrant 1, or another way to describe that is using an infinity notation. We could say as x goes to negative infinity, that means as we move forever to the left, I see that this function, its y value, would be going up to positive infinity. And as x goes to positive infinity, that means as the function moves to the right, what's happening to the y values? Well, they're going up again. They're going up to positive infinity. So these are two different ways of describing a function's end behavior. So what would happen if we still have an even degree function, but its leading coefficient is now negative? That would vertically reflect a polynomial function so that it's now starting down in quadrant 3 and finishing down in quadrant number 4. So we could communicate that end behavior two different ways. We could say the function goes from quadrant 3 to quadrant 4. We always state these quadrants in an order so that it goes from where the function starts, its leftmost quadrant, to where it finishes, its rightmost quadrant. Or we could describe it using infinity notation by describing what happens to the y values as x goes to negative infinity, and also as x goes to positive infinity. As x goes to negative infinity, that means as we move to the left along the function, the y values are going down to negative infinity. And as x goes to positive infinity, so as we move along the function to the right, the y values of the function are going down to negative infinity. So for any even degree polynomial function, what you're going to find is that the end behaviors are the same, meaning that both sides are pointing up if we have a positive leading coefficient, or both sides are pointing down if we have a negative leading coefficient. But what happens if we have an odd degree polynomial function? Let's start with an odd degree and a positive leading coefficient. If we have that, the function is going to start down in quadrant 3 and finish up in quadrant 1. So as x goes to negative infinity, as we look at the function's behavior, as we move to the left, the function is going down to negative infinity. But as the function moves to the right, we notice that it starts going up towards positive infinity. And our last scenario is if we have an odd degree polynomial function, but we vertically reflect it by making the leading coefficient negative. That would make it go from quadrant number 2 down to quadrant number 4. And I'll quickly write this in infinity notation as well. Notice, for any odd degree polynomial function, the end behaviors are opposite. One side's going up and the other side's going down. The y values are going to negative infinity on one side and to positive infinity on the other side. And now let me make some room so we can do a couple examples where we test out if you're able to state the end behavior of polynomial functions. Let's do an example where we state the end behavior of each of the following. Part A, we have the graph of a function, and I can clearly see from the graph that its left side starts in quadrant number 2, and then its right side finishes down here in quadrant number 4. So this function's end behavior is from quadrant 2 to quadrant 4. And I don't see its equation, but because of that end behavior, I would actually know a little bit about its equation. Because it has this end behavior, I know that it is an odd degree polynomial function with a negative leading coefficient. And in part B, we just have the equation, we don't have the graph. But from the equation, if I look at the highest degree term, I see that it is degree 5, which is an odd degree, and the coefficient of the highest degree term, its leading coefficient, 3, is positive. So because of those two criteria, I know it is this scenario where the function starts in quadrant 3 and finishes in quadrant 1. And then for part C, here's my highest degree term. Its degree is 4, which is an even degree. And the coefficient of that highest degree term, the leading coefficient, is negative 1/2. So the leading coefficient is negative. Because of those two pieces of information, I know we have this scenario where it goes from quadrant 3 to quadrant 4. And before we move on, one last tip for you. If you look at the right side of any function, if the right side is pointing up, you know you have a positive leading coefficient. And if the right side is pointing down, you know you have a negative leading coefficient. And if both sides are pointing in the same direction, either both up or both down, it's even degree. But if both sides are pointing in opposite directions, it's odd degree. Must know number 3. X-intercepts and turning points. A degree n polynomial function can have, at most, n x-intercepts. Now there's something called the fundamental theorem of algebra, which tells us that a polynomial function of degree n has exactly n roots, or n zeros. So why doesn't it have exactly n x-intercepts? Well, there might be fewer than n x-intercepts if there are repeated or non-real roots. Right? Only the real roots or real zeros of a polynomial correspond to an x-intercept. And let me give you a quick demonstration of the possibilities for the number of x-intercepts, let's say a degree 3 polynomial function could have. A degree 3 polynomial function could look like this, where there are 1, 2, 3 x-intercepts, that's the most it could have. But if it has a repeated root, you'll see the shape at an x-intercept change, so it could look like this, where there are only 1, 2 x-intercepts. Or there could be a pair of imaginary roots, which would make it only have 1 x-intercept like this. But having 0 x-intercepts wouldn't be an option. And actually, it's not an option for any odd degree polynomial, because an odd degree polynomial starts and finishes on opposite sides of the x-axis. It has to cross at least once. So let's add that information to our table as well. And now let me erase this graph and shrink this writing here so we have room to talk about turning points. A degree n polynomial function can have at most n minus 1 turning points. So, for example, a degree 5 polynomial function could have at most 1, 2, 3, 4 turning points. That's the most it could have. Could a degree 5 function have 3 turning points? Let's think about that. I know degree 5 is an odd degree, so it would start and finish on opposite sides of the x-axis. If I were to only turn 3 times, 1 time, 2 times, 3 times, notice that the function is heading in the wrong direction. That would have the wrong end behavior. So what I'm trying to demonstrate to you is an odd degree polynomial function has to have an even number of turning points. So an odd degree polynomial could have 0, 2, 4, or so on, up to whatever n minus 1 is equal to. Those are the possibilities for the number of turning points it could have. And then similarly, an even degree polynomial has to have an odd number of turning points. So an even degree polynomial could have 1, 3, 5, or so on, up to n minus 1 turning points. And now let me make some room and let's do an example where we look at some equations and graphs and look at how many x-intercepts and turning points they have. The first example, we have the graph of a function, and we're just looking for how many turning points does it have, how many x-intercepts, and what is the degree of the polynomial. A turning point is a place where the function switches between increasing or decreasing or vice versa. And I see that happening in 1, 2, 3, 4 places on this polynomial. So it has 4 turning points. How many x-intercepts does it have? I see it touch the x-axis 1, 2, 3 times. So there are 3 x-intercepts. So what degree could this polynomial be? Well, it has 3 x-intercepts, so could it be degree 3? No, it couldn't be degree 3 because a degree 3 could have at most 2 turning points. Could it be degree 4? Well, a degree 4 could have at most 3 turning points, so no. And also, I can see based on this end behavior that this is odd degree. So the least possible degree this function could be is degree 5. Now let's look at example 2 where we have the equation of a degree 4 polynomial function. An even degree polynomial function has to have an odd number of turning points. So the possible number of turning points this function could have, well, I don't have the graph of it, so I don't know exactly how many turning points it could have, but I know the options for what it could have are either 1 or 3 turning points. And the possible number of x-intercepts? Well, the most it could have is equal to the degree, or any number less. So it could have 0, 1, 2, 3, or 4 x-intercepts. Notice 0 is a possibility for the number of x-intercepts of an even degree polynomial, but it wouldn't be an option for an odd degree. So in example 3, where we have a degree 7 polynomial function, the possible number of turning points, since it's odd degree, would be any even number less than 7. So 0, 2, 4, or 6. And the possible number of x-intercepts At most is 7 or any number less, but we can't include 0 for an odd degree polynomial. So 1 all the way up to 7. Must know number 4, even and odd symmetry. In this section, I'll explain to you the characteristics of even functions and odd functions. Let's start with even functions. We've talked about even degree functions, but not all even degree functions can be further classified as an even function. An even degree polynomial function is an even function if its graph has line symmetry over the y-axis, and in its equation, every single term is an even degree term. Now, because of this line symmetry over the y-axis, there is an algebraic rule that would hold true for any even function. The rule states that the value of f at x would be equal to the value of f at negative x. And I'll be able to explain that more to you as I show you an example of an even function. So here's the function we're going to work with. This polynomial is even degree because the highest exponent is 4, but it can also be further classified as an even function because every single term is even degree. We have a degree 4 term, a degree 2 term, and a degree 0 term. Those are all even. Which means if we look at its graph, we would see that there is line symmetry over the y-axis. Which means algebraically this property must be true. So for example, if I were to evaluate f at 2, subbing this 2 in for the x's into my equation, I would figure out that f at 2 is equal to 2. That means this point right here is the point 2, 2. Because this is an even function, I know it's got line symmetry over the y-axis. So moving 2 units to the right, my point is at a height of 2. And because this is an even function, I know this property holds true, which tells me that if I were to move 2 units to the left, the height would also be at 2. And if you were to evaluate f at negative 2, you would get an answer of 2 as well. Which means this point is the point negative 2, 2. Now before we move on, make sure you understand that not all even degree functions are even functions. For example, if I took this function here and I threw another term into it, I've added this x cubed term. Now this equation has a mix of even and odd degree terms. The yellow terms are all even degree, but this blue term is odd degree. That means that this even degree function is not an even function. So let me take this term back out and then we'll move on to odd functions. For odd functions, an odd degree polynomial function is an odd function if its graph has point or rotational symmetry at the origin, and in its equation, all the terms are odd degree. And algebraically, it would follow the rule that says the value of f at negative x is not equal to f at x, but instead equal to the negative of f at x. And now let me clarify all of this with an example. For this equation, I see the highest exponent is 3, so this is an odd degree polynomial function. But what also makes it be further classified as an odd function is that every single term that makes up this function is odd degree. We have a degree 3 term and a degree 1 term. Those are both odd values. So I know that its graph would have point, or what's sometimes called rotational symmetry, about the origin. And let me try and show you what that looks like. So pay attention, as I rotate this function 180 degrees around the origin, notice that it lines back up with the original function exactly. That's what point symmetry is. And because it's an odd function, I know this rule would hold true. And let me demonstrate that to you. If I were to evaluate f at negative 3, subbing that negative 3 into my function for x, I would calculate that the y value is negative 15. So let me put that approximately on my graph. Moving 3 to the left of the origin, my point has a height of negative 15. If this was an even function, I would expect moving 3 to the right, my point would also have a height of negative 15, but the function is not down here. It's actually up here. When I evaluate f at 3, I actually get positive 15. So the point 3, positive 15 is on the graph. Now look at the relationship between the y values of these answers. This one's negative 15, this one's positive 15. So multiplying this one by negative 1 would make it equal to this one. And that's exactly why this negative is in our rule. So to make these values equal, I would just multiply this function by negative 1. So negative f at 3 would be equal to negative 15. Must know number 5. The factored form equation of a polynomial function. The general structure of a factored form polynomial equation looks like this. And what makes this a factored form equation is the equation is just a product of a bunch of factors. This factor of a is just a non-zero constant. These r parameters are just the roots of the equation, because subbing in any of the values that you would see here for r, subbing those in for any of the x's, would make one of the factors become 0, which makes the whole product become 0. So that's why they're the roots, or the zeros, of the function. And any of those r values that are real numbers, they're going to show up as x-intercepts on the graph. The exponents that we see on the factors that contain an x are the multiplicities, or the orders, of the roots. So basically these exponents are just a way of describing how many times the root of that factor is repeated. And the degree of a factored form polynomial function is equal to the number of roots or number of zeros the equation has, counting their multiplicities. So let me give you a couple quick examples of that to make sure you understand it. Now this factor would be 0 if x was 2, which means 2 is a root of this equation. And since this factor is repeated 3 times, we say the root of 2 has a multiplicity of 3. The root of 1 has a multiplicity of 2, and this factor will be 0 if x was negative 4, so the root of negative 4 has a multiplicity of 1. To find the degree of this polynomial function, we have to add up all the roots counting their multiplicities. So we would have to do 3 plus 2 plus 1, which is 6. So this is a degree 6 polynomial. Let me make a little more challenging one. Now this polynomial is in factored form. It's a product of these factors. Since the degree is equal to the number of roots counting their multiplicities, well, I know this factor would be 0 if x was a half. So a half is a root, and it's repeated 2 times. But this factor doesn't have any real roots. That's okay, it does have 2 imaginary roots. So we do include those when adding up the number of roots. So this factor has 1 root, but it's repeated twice, we count that as 2 roots. And this factor has 2 imaginary roots, so we count those as well. So 2 plus 2 is 4, so this is a degree 4 function. And let me actually erase those examples we just did, so that I have room to tell you about how the orders of the roots that cause the x-intercepts affect the shape of the graph. First of all, it's worth writing down that all the real roots correspond to the x-intercepts. Any imaginary roots don't show up as x-intercepts on our graph. And the order of those real roots affect the shape at the corresponding x-intercept. And then I'll draw a quick sketch of the shape of a couple different orders of x-intercepts. If a root of the equation is order 1, we would say that its corresponding x-intercept is order 1, which means at that x-intercept, it's going to look exactly like a degree 1 power function, which is just a straight line. So it would go straight through an x-intercept of order 1. But if the x-intercept is order 2, that means at the x-intercept, it's going to look like a degree 2 power function, which is a parabola. So we know it would bounce off just like this. And at an x-intercept of order 3, it'll look like a degree 3 power function, which makes this S shape through the x-intercept. And I should also mention that any even order higher than order 2 is going to have a similar shape to this at the x-intercept, where it just bounces off the x-axis. But the higher the order is, the flatter that it's going to get around the x-intercept. And the same thing for odd orders. Any odd order higher than order 3 is still going to make this S shape through the x-intercept, but the higher the order is, the flatter that it's going to get around that x-intercept. And now let's try an example where I give you a factored form equation, and we state a bunch of properties and do a rough sketch of its graph. So for this polynomial function that's in factored form, we're going to state a bunch of properties. Let's actually start with the x-intercepts. The x-intercepts are the real roots of the equation, so the real values of x that make the equation 0. Well, a factored form equation would be 0 if any of the factors were 0. X minus 1 would be 0 if x was 1, and because the exponent on the factor that creates that x-intercept is 1, we would say that x-intercept is order 1. This factor could be 0 as well. And if you needed to, you could make yourself a little equation, solve the equation for how it could be 0, and you would figure out it would be 0 if x was negative 5 over 2, which is just negative 2.5. And the factor that creates that 0 is repeated 3 times, which means that x-intercept is order 3. And this factor would be 0 if x was 2, and that factor is repeated 2 times, so the x-intercept of 2 is order 2. Now let's find the degree. The degree is equal to the number of roots, including their orders. This equation had 3 roots. If I add their orders together, 1 plus 3 plus 2, I get 6, which means the degree of this equation is 6. Now to find the leading coefficient, that means if we were to put this into standard form by fully expanding it, what would be the coefficient of the x to the 6th term? We could find that coefficient without fully expanding, just by multiplying, first of all, the constant factor with the coefficients of all of the x's in any of the factors, remembering to include the exponent that is on those coefficients. So I would do 1/4 times 1 times 2 cubed times 1 squared. And evaluating this, you would get an answer of 2. Now end behavior. We have an even degree with a positive leading coefficient. I know that goes from quadrant 2 to quadrant 1. And we've already found the x-intercepts with their orders. Let me change the color of this to yellow to keep it consistent. And now let's calculate the y-intercept. I know wherever it crosses the y-axis, the x value is going to be 0. So to find the y-intercept, all I have to do is evaluate p at 0. And if you do that, you get negative 125. So the y-intercept is at the point 0, negative 125. And with all this information, we could sketch a fairly accurate graph of this function. I'll start by roughly plotting the x-intercepts, and then use my end behavior, which tells me I need to start in quadrant 2 and finish in quadrant 1. And at each x-intercept, make the shape that the corresponding order tells me it has to make. So for example, at my first x-intercept of negative 2.5, that's order 3, so I have to make this S shape. And then I'll continue the function, and as I approach my next x-intercept, this x-intercept of 1 is order 1, so it has to go straight through. And then my last x-intercept of 2 is order 2, so it has to make this parabola shape at that x-intercept. So there we have a fairly accurate graph of this polynomial function. Must know number 6, how to find the equation of a polynomial function from its graph. Let's find the equation of this polynomial function in factored form. To write the equation in factored form, we'll have to give the function a name. We'll call it p at x, and that's equal to, there's going to be some constant factor, we'll call it k, being multiplied by a bunch of factors that contain an x. And I'm going to leave room for 3 factors, and the reason why is because on the function, I see 1, 2, 3 x-intercepts. The first x-intercept is at negative 4, and I notice at that x-intercept, it makes this parabola shape where it bounces off the x-axis, so I know that x-intercept must be order 2. And then the x-intercepts at both 0 and 3, the function just passes straight through those x-intercepts, so they're both order 1. And now we have to use each of those x-intercepts to figure out what factors go in the equation. Each of these x-intercepts would be a 0 of one of the factors that are in the equation. So let's start by figuring out what factor would be 0 if x was negative 4. So to do that, I'll start with my answer. I know x is equal to negative 4 when some factor is set equal to 0. To figure that out, let's reset it back to 0 by moving the negative 4 to the other side. And I figure out if the factor was x plus 4 equal to 0, that would be true if x was negative 4. So x plus 4 must be a factor in my equation. And because it's order 2, I know I have to put an exponent of 2 on that factor. And now I'll do that same process for both of these x-intercepts. I'll set them as the answers, x equals 0 and x equals 3, and then figure out what factor has those as their zeros. Well, for this one, I'll move the 3 to the other side, and I figure out if the equation was x minus 3 equals 0, then the answer would be x equals 3. So one of my factors must be x minus 3. And then this one is already set equal to 0, so that factor must just be x. And now hopefully you can see what we did is we created an equation in factored form where any of these values would make the whole equation be 0. Negative 4 would make this factor be 0, 0 would make that factor be 0, and 3 would make that factor be 0. And in factored form, if you can make any of the factors become 0, it makes the whole product become 0, meaning they are x-intercepts of the graph. But there are an infinite number of polynomial equations that could have those factors containing those x's and create those same x-intercepts. We want the very specific version that passes through this point that we see here, the point 1, 5. That point has an x and a y value. So what we can do in our equation, we can set the x's equal to 1, and we can set the y value equal to 5, and then solve for what value of k stretches our function to be able to go exactly through that point. So I'll set y to 5, and then change all of the x's to 1. And now we just have to isolate for k. So I have 5 equals k times 5 squared, which is 25, times 1, I don't have to write a factor of 1, times negative 2. On the right side of my equation, I have k times negative 50, which I'll write as negative 50k. And then to isolate k, I would just have to divide both sides by negative 50. Those cancel. And I figure out that k equals 5 over negative 50, which could simplify to negative 1 over 10. And now I can write my final equation of the polynomial function. P at x equals, my constant factor is negative 1 over 10, multiplied by all 3 of these factors that contain the x. When you have a factor of x all by itself, typically you write that first, and then the other 2 factors. And there's our final answer. Must know number 7, synthetic and long division. These are 2 methods for dividing polynomials. Let's start with long division. Let's say we want to do 4x cubed plus 9x minus 12 divided by 2x plus 1. To do this division, we can set up our division table. Underneath the table, we write the dividend. And notice a couple things about that dividend that I wrote. I added in a 0x squared as a placeholder, because when we do this method of long division with polynomials, we want to make sure that we have a place for every degree equal to and less than the degree of the polynomial. So if the degree of the polynomial is 3, I'm going to need a column for degree 3 terms, degree 2 terms, degree 1, and degree 0. But we were missing degree 2, so I threw in a 0x squared there as a placeholder. And the second thing I want you to notice is that we put the terms in descending order based on degree. From the highest degree, 3, down to the lowest degree term, the degree 0 term. And then we write the divisor, the 2x plus 1, outside the table. And our answer, our quotient, is going to go at the top of the table. Now the process for long division with polynomials goes as follows. Step 1, first term of the dividend divided by first term of the divisor. So I have to do 4x cubed divided by 2x. Dividing the coefficients 4 and 2 gives me 2. And dividing the variable parts of those terms, x cubed divided by x to the 1, the quotient rule tells me to keep the base of x and subtract their exponents. 3 minus 1 is 2. So I get 2x squared as the quotient of those two terms. And what I want to do now is multiply this term in the quotient by the entire divisor. So the 2x squared has to be multiplied by 2x and 1, and write the answers down here in the dividend lined up in columns with their like terms. So 2x squared times 2x is 4x cubed, and 2x squared times 1 is 2x squared. Notice how like terms with the same exponents on their variable, are lined up with each other in columns. And what we do is we subtract the like terms that are in our dividend. The first pair of terms should cancel out if we've done things properly. 4x cubed minus 4x cubed is 0. And 0x squared minus 2x squared is negative 2x squared. We can then bring down the next term in our dividend. We can actually bring down all of the terms that we have left in the dividend if we want, but we're only going to need one more for the next step, so I'll bring down the 9x for now. And then we repeat the process. We do the first term that's in the dividend, so negative 2x squared, and divide it by the first term of the divisor. Negative 2x squared divided by 2x is negative x. And then that negative x gets multiplied by the whole divisor. And then in the dividend, we subtract our like terms. We then bring down our last term of negative 12 and repeat the process one more time. 10x divided by 2x is 5. And then multiply this 5 by 2x plus 1 to get 10x plus 5. And when subtracting like terms there, all I'm left with is negative 12 minus 5, which is negative 17. So that's what we call the remainder of this quotient. Once your dividend is a lower degree than your divisor, you know that you're done the division process and what you have left in the dividend is the remainder. So there are a couple different ways to express this answer. I'm going to show you how to express this in what's called quotient form. We could say that the original division question is equal to the quotient plus the remainder over the divisor. And now let me make a bit of room and show you another method that is a little bit of a shortcut that only works in certain situations. And this method is called synthetic division. Now, synthetic division only works to divide a polynomial by a linear divisor of the format x minus b. And what that means is we can only divide by a polynomial that is degree 1 with a leading coefficient of 1. So for example, we could do this division question using synthetic division. Our divisor is degree 1 with a leading coefficient of 1, so that's perfect for synthetic division. And how synthetic division works is we set up a table. I take the coefficients of all of the terms in my dividend and I write them across the top. And then I take the 0 of my divisor and write it up here. So what makes x plus 3 be 0 would be if x was negative 3. And then I'm going to write a multiplication operator here and an addition operator here so that I can remember what steps to follow when doing synthetic division. Step 1, you take the first number in your dividend and you rewrite it at the bottom here. That's going to be the coefficient of the first term in our quotient. And then to get the remaining coefficients, we follow this process where we do negative 3 times 6 and write the answer in the next column. Negative 3 times 6 is negative 18. I then add the numbers in this column. 13 plus negative 18 is negative 5. And then just repeat the process. Negative 3 times negative 5 is 15. Negative 34 plus 15 is negative 19. Negative 3 times negative 19 is 57. Adding those numbers gives me 10. Negative 3 times 10 is negative 30. And then adding those numbers gives me negative 2. Now the far right number is our remainder, and then the rest of the numbers are the coefficients of the terms in our quotient. Starting from the right, the first number is the coefficient of my degree 0 term, then my degree 1 term, degree 2, and degree 3 term. So this is my quotient, and this is my remainder. We could write that just like the last one in what's called quotient form, or there's another way. We could write it in its multiplication statement form. And how that would look, you would split up the original dividend into a product of the divisor and the quotient plus the remainder. Must know number 8. The remainder, 0, and factor theorems. In order to be able to use those tools of synthetic and long division to get a polynomial function into its factored form, we're going to have to understand 4 theorems that I'm going to show you here. The first one is called the remainder theorem. The remainder theorem says if p of x is divided by x minus b, the remainder is equal to p at b. So basically this is saying if we take the 0 of the divisor, right, x minus b would be 0 if x was b. If we take that and we sub it into our polynomial function for x, we get what the remainder is if we were to do the division. So we could extend this a bit further. If we divided by ax minus b, the remainder would be equal to, well, we'd have to sub the 0 of that divisor into p at x. And what makes ax minus b be 0? If we isolate for x, we'd have ax equals b, which means x equals b over a. We would just take that, sub it in for x, and that would give us the remainder. So it would be equal to p at b over a. And let's do an example to see how this works. The example says, what is the remainder when dividing this polynomial function by x plus 1? To find the remainder, I don't have to do the whole long or synthetic division. I can just take the 0 of the divisor, well, x plus 1 would be 0 if x was negative 1, and sub it into this function for x. So I just have to evaluate what is p at negative 1. Replacing all the x's with negative 1, I get an expression that if I were to evaluate it, it tells me the remainder. And evaluating this, I figure out the remainder is negative 4. And now I'll make some room and show you the factor theorem. The factor theorem is actually just an application of the remainder theorem. It tells us that x minus b would be a factor of p of x if, well, for x minus b to be a factor of p of x, that means it divides evenly into it. Or another way of saying that, if we were to do p of x divided by x minus b, we should get a remainder of 0. So how could we check if there's a remainder of 0? We could take the 0 of the divisor, x minus b would be 0 if x was b, and sub that into our polynomial function. So x minus b would be a factor of p of x if p at b was equal to 0. And then we could extend that one step further and say ax minus b would be a factor of p of x if when dividing them we get a remainder of 0. And we could check their remainder by taking the 0 of ax minus b, which is b over a, and subbing it into our p of x function. So that would be if p at b over a was equal to 0. And let's do an example to see how this works. So this example says, is x minus 3 a factor of this polynomial? It would be a factor if, when I divided this polynomial by x minus 3, I got a remainder of 0. And I can check to see if it has a remainder of 0 by just subbing in the 0 of x minus 3. Well, x minus 3 would be 0 if x was 3. So just take that value of 3 and evaluate the polynomial function at that value of 3. And when I evaluate this, I get 0, which means the remainder is 0, which means x minus 3 is a factor of the polynomial. And now I'll make some more room and give you the last 2 theorems. So the next theorems that I want to show you are the integral 0 theorem and the rational 0 theorem. The integral 0 theorem states that if b is a 0 of p of x, then b is a factor of its constant term. And the best way for me to explain that is with an example. For this function p at x, this polynomial is degree 3. So based on the fundamental theorem of algebra, I know there are 3 zeros to this equation. But some of the zeros might be repeated, or some of the zeros might not even be real. But if any of the 3 zeros of this equation are integers, I know that those integers would be factors of the constant term. So the possible integer zeros of this equation are factors of negative 6. So what numbers divide evenly into 6? Well, it could be plus or minus 1, 2, 3, or 6. So the positive or the negative of any of those 4 numbers would divide evenly into our constant term of the polynomial. Which means if there are any integer values that make that polynomial be 0, they would be found in this list of 8 numbers. What about the rational zero theorem? If b over a is a zero of p of x, then b is a factor of the constant term and a is a factor of the leading coefficient. Let me explain this in more detail with an example. I'll make a little bit more room. And then let's write a polynomial function. If I was interested in what integers might make this function be 0, I know the only integers that would make it be 0 would be factors of the constant term. But I could write a more comprehensive list of the possible zeros. If I used the rational zero theorem, it would allow me to make a complete list of all rational numbers that might make it be equal to 0. And I can do that by doing factors of the constant term. So factors of -6 are plus or minus 1, 2, 3, or 6. And dividing each of those by the factors of the leading coefficient. The factors of 2 are plus or minus 1 and 2. So I have to take each of those 4 numbers and divide them by each of those 2 numbers. And that will give me my whole list of possible rational zeros of that polynomial. So I would have plus or minus. I have to do this 1 divided by both 1 and 2. So I'll have 1 over 1, which is 1, and 1 over 2. Then I need to do this 2 divided by both 1 and 2. 2 divided by 1 is 2, and 2 divided by 2 is 1, but I already have that written here. And then this 3 gets divided by both 1 and 2. And then this 6 gets divided by both 1 and 2 to give me 6 and 3, but I already have 3 written. So if there are any rational numbers that make this polynomial be 0, they will be found in this list. And now that you know all 4 of these theorems, we can apply them to be able to solve some polynomial equations and inequalities in the last couple sections of this video. Must know number 9, solving polynomial equations. Let's solve these 2 equations. Starting with the equation on the left, I want to know when is this degree 3 polynomial equal to 0. Based on the fundamental theorem of algebra, I know this polynomial has 3 zeros. Some of those zeros might be integers, some might be irrational numbers, some might be complex numbers, and some might even be repeated. But in order to find them, we want to try and get this polynomial into factored form. But in order to do that, I'm going to have to find one of the zeros of this equation so that I can decide what to divide the polynomial by to get it into factored form. But I don't just have to guess and check any number that might make it be 0. I know based on the integral zero theorem that if there is an integer that makes the polynomial be 0, it would be a factor of the constant term. So the possible integer zeros of this equation are factors of 10, which would be plus or minus 1, 2, 5, or 10. Now, up to 3 of these numbers might work. I just have to find one of them that works. So we just test until we find one that makes the polynomial be 0. The first test I'll test 1 in the equation. So I'll replace all the x's with 1. And if I evaluate this, it actually does equal 0. Since 1 makes this polynomial be 0, I know that one of its factors would have to be x minus 1. And that's because this factor would be 0 if x was 1. So I can start the factoring process by rewriting this equation, and then I can split that polynomial into 2 factors. The first factor is x minus 1, and then the second factor would be whatever the quotient is when I divide that polynomial by x minus 1. And I can do that division with either long division or synthetic division. I'll quickly do a synthetic division off to the side by writing the coefficients of that polynomial up here, and the 0 of x minus 1 right here, and then run the synthetic division algorithm, which tells me to bring the first term down, do 1 times 1, which is 1, and then add the numbers in this column to give me -3. And then if I repeat that process until I'm done, I get the following answer. Getting 0 for the remainder verifies that x minus 1 is a factor of the polynomial, and the other factor is the quotient x squared minus 3x minus 10. And now that I have the polynomial in factored form, I have a product of 2 things equal to 0. I know that product would be 0 if either of these factors was equal to 0. This factor would be 0 if x was 1. And to figure out when this factor would be 0, I could either use quadratic formula or I could continue factoring it. So I think I'll continue factoring it. I just have to find numbers that multiply to -10 and add to -3. The numbers that satisfy that product and sum are -5 and 2. So that means I could further factor that quadratic into x minus 5 times x plus 2. And now that the polynomial is fully factored, the product would be 0 if any of the three factors would be 0. This factor would be 0 if x was 1, this one would be 0 if x was 5, and this one would be 0 if x was -2. So those are all answers to this equation. I'll write them in ascending order. And you could verify any of those answers just by checking them in the original equation to make sure it makes left side equal right side. Let's move on to the second equation, the one on the right. The first thing I notice is that it's not set equal to 0, it's set equal to -12. So we'll start by moving that -12 to the other side. And now that the polynomial is set equal to 0, we want to get the polynomial into factored form. But for this one, we actually don't have to do a test of the possible zeros and then do a synthetic division to get it into the factored form. There's actually a shortcut for this one that's called factoring by grouping. For factoring by grouping, you look at the first two terms, take out a common factor, so I could take out an x squared from the first two terms, and when I divide them both by x squared, I get x minus 3. And then for the last two terms, we take out a common factor as well. From the last two terms, I could common factor a -4. And when I divide them both by -4, I get x minus 3 again. Getting this common binomial means that factoring by grouping is working. In the first term, there's an x minus 3, and in the second term, there's also an x minus 3. So what we can do is we can common factor out that x minus 3. And when I divide both of those terms by x minus 3, it cancels them out, and we're left with x squared minus 4 as the second factor. And this x squared minus 4 is a difference of squares. It's an x squared minus a 2 squared, so it would factor to x minus 2 times x plus 2. And now that this is fully factored, the product would be 0 if any of the three factors were 0. This one would be 0 if x was 3, this one if x was 2, and this one if x was -2. So I'll write all three of those answers in ascending order. Must know number 10, solving polynomial inequalities. When solving an inequality, we want to start by moving all of the terms to one side. So I'll move the terms from the right over to the left. And now we're interested in when is this polynomial less than or equal to 0. So graphically speaking, that means when is it below the x-axis. So to figure that out, I'll sketch a graph of this that includes the proper x-intercepts and end behavior, and then I'll be able to answer the inequality. I know the x-intercepts correspond to the zeros of that polynomial, and I can find those if I get it into factored form. And to get it into factored form, I'm going to first have to test and find one number that makes it be 0, so that I can decide what to divide it by to get it into factored form. Based on the rational zero theorem, I know that if there's a rational number that makes this be 0, it's going to be a factor of the constant term divided by a factor of the leading coefficient. The factors of 6 are plus or minus 1, 2, 3, or 6, and the factors of 5 are just plus or minus 1 or 5. So to make my whole list of possible rational zeros, I do each of these 4 numbers divided by each of these 2 numbers. So of these 16 numbers that are here, because this is degree 3, I know that up to 3 of these could make it be 0. I just have to find one of them that works. So I'll do a test, and I'll show you that -1 actually makes it be 0, which means that a factor of the polynomial must be x plus 1, because x plus 1 is 0 when x is -1. So I can now split this polynomial into 2 factors, a factor of x plus 1, and then some other factor that is the quotient of this polynomial and x plus 1. So I'll do that division. I can do that using synthetic division. I'll do that off to the side here. I'll use the coefficients of that polynomial, and then the 0 of the divisor is -1, and then running the synthetic division, I see that the quotient is 5x squared minus 17x plus 6, so I can write that here as my second factor of the polynomial. And then I'll want to factor the quadratic further by finding numbers that have a product of 5 times 6, so a product of 30, and a sum of -17. The numbers that work are -15 and -2. So I can split this middle term into -15x minus 2x. and then factor this quadratic by grouping. I'll leave the x plus 1, but then I take a common factor from the first two terms. I'll take out a 5x. And then from the last two terms, I could common factor a negative 2. I'll leave the x plus 1 again, and then common factor this x minus 3 from both terms, leaving me with 5x minus 2. Now that it's fully factored, I could easily see when this polynomial is equal to 0. It would be 0 if x was either negative 1, 3, or 2 over 5, which means the x-intercepts of this polynomial would be at negative 1, 2 over 5 is 0.4, or 3. So now that we have the x-intercepts of this polynomial, we should be able to sketch a graph using its proper end behavior to figure out when it's less than or equal to 0. But what is the end behavior of an odd degree polynomial function that has a positive leading coefficient? Remember, that would go from quadrant 3 to quadrant 1. So I'm going to erase what I've got over here so that I have some room to sketch my graph and answer my inequality. I'll make a Cartesian grid. I will plot my x-intercepts roughly, and then using this end behavior, I know it has to start down here in quadrant 3 and finish up here in quadrant 1, which means it's going to look something like this. And we want to know, when is this polynomial less than or equal to 0? So basically, when is it below the x-axis? It's below the x-axis in this interval and in this interval. So let's describe those two intervals as our answer to the polynomial inequality. This section of the function is when x is less than or equal to negative 1, and this section of the function is when x is between 0.4 and 3. So we could describe those intervals with inequality symbols like this, or we could write it in interval notation by saying x is an element of numbers between negative infinity and negative 1, or from 0.4 to 3. And notice I used square brackets at each of the x-intercepts because at those x-intercepts, this polynomial is equal to 0, and the original inequality states we want to include when it's equal to 0. So hopefully you learned a lot about polynomial functions in this video. Let me know what you want a top 10 about next.
Jensen Math!